Next speaker. I think we need to change the PC again or no? Okay, so it's okay. So the next speaker is Suman Bajracharya from my institute Vito in Belgium, and he is going to speak about the application of gas diffusion electrodes for CO2 reduction in microbial electrosynthesis.
Okay, hello everyone, and I'm Suman Bajracharya from Vito, the institute, research institute in Belgium, and I'm a PhD student in Wageningen University in Netherlands. My talk today is on application of gas diffusion electrode for and flow-through electrodes for CO2 reduction in microbial electrosynthesis. First, okay, we'll go with the. First, we'll go with some introduction. Now, microbial electrosynthesis. It's a very new, the new dimension for the bioelectrochemical system, where we can produce important compounds using the waste or low-value compounds at a cathode. And in this system, the electrons, the source of electrons, we can get it in an anode, like. Here in the figure, we can use water oxidation at the anode, and the electrons produce and protons also produce. And the electron, we can drive it to the cathode using some power from renewable sources. And then at the cathode, we can use the electrons for the reduction of CO2 using this biocatalyst bacteria. And after this, the CO2 reduction and the product, we can use it into the extraction and separation, and we get some important compounds. For this process, what we see is we are applying the potential in the cathode. So that's when you apply a potential, so there are some routes for the reduction. So one is if we apply a potential of minus 0.48 or 0.58, then we can see this is the redox potential for the reaction. But if we use more potential because of the over potential of electrode, we need to apply more power. Then we see the hydrogen evolution. So, whatever is a route, but we can use it when we use more negative potential. Then we can get this reduction either direct electron transfer through the bacteria or with the hydrogen. Now, okay, this is just for the way how to develop the biocatalyst. So in our system, what we did is we used the sludge, and the sludge was heat shock for 60 minutes at 90 degrees centigrade. So that's why we can kill the methanogens that we don't need it. And then with the fermentation with the fructose, we can revive those that's from the spores. And then with the enrichment phase with the CO2 and S2, we can adapt them really into the homoacidogenous rich system. And now, okay, these are the biocatalysts and the process. But what we need now is about the electrode. So in this electrode, what we need for CO2 is the first experiment we did at the start. It just produced 0.6 gram per liter of acetate. That's quite low, but we need to improve it. So in that sense, what we saw is that the CO2, when we dissolve in water, aqueous medium, then the solution is only 1.5, around 1.5 gram per liter. So there could be some CO2 limitation for the bacteria to get it. There are two ways, like you have to dissolve it into liquid, and then the liquid that should go into the bacteria. So there are two ways of limitation. So and then if we think about application, we need to use a waste gas. So, but waste gas not always has 100% CO2. It has much more, or maybe it has less, like 20%, 15%. And we apply 100% CO2, then we are wasting more than what is converted into a compound. And other thing we need for electrode is it should give a right amount, a sufficient amount of electron and bioelectrochemically produced hydrogen. That's what we needed for an electrode. And out of that, normally when we use it's this kind of bottle MFC, that's normally what we saw from the beginning. So when we put the gas, we put like just a bubbling or sparser, like normal fish. So this sparging, is it good enough to give the bacteria right amount of CO2? So that's the question. So when we analyze that, then we come up with two design. So one is using a gas diffusion electrode here, and when we use a gas diffusion electrode, the CO2, when we apply from here, so we put some pressure, and then it's diffused into it. So not only diffusion, advection is also applied in this case. So this is one design, and another one we are proposing is a flow-through electrode, where this dissolved CO2 we are normally sparse with the sparser, and dissolve the whole catalyte. We can pass it through a porous electrode. So that's two options that we try here. Yeah, and first we go through the first one, the gas diffusion electrode. This gas diffusion electrode is that's the previous speaker. He also mentioned there's a hydrophilic and hydrophobic pores. So it gives a medium for three phase contact, like solid, gas, and liquid. So three can come in the same place. So bacteria can interact very well with the substrate and the liquid. So, but this electrode has already been used in MFC, and it's proved very, it was effective, and it was published by Zhang et al. And so the same one, we use it here for CO2. I have some samples. If you need it, if you can come to see if we'll have some samples. And yeah, here this electrode we have PBMF, PTFE, and this is a PTFE plus carbon activated carbon layer. So that's from the company. The Vito, we make it like in the standard way. Now for this electrode, so we first test with how good they are. So when we compare this gas diffusion electrode and normal sparging, the CO2 transfer, so we did some tests on the oxygen transfer. So when we use this test, it's like the slope of this curve will give the how good is the KLA value. That's the mass transfer coefficient value. So when we calculate this, then with GE we got 3.9 per hour, and for direct sparging we get 1.9. So that means we have 2 times faster diffusion. The mass transfer is double. So this already proved that GDE is better for dissolving the gas. And when we apply in the cell with the bacteria, yeah, this is a quite a long-term experiment. And first we apply with a 20% CO2, and we see yeah, after 50 days, after the growth and the bacteria growth, then we start with the experiment on 55 days. So the acetate, it started producing acetate, and it goes up till 2 gram. So maximum concentration goes up to 2 gram, and the rate of production, the maximum is 238 milligram per liter per day. So that was higher than what we have produced before. Previous was only 0.6 gram per liter. And then what we see here, this is the current, and yeah, after some time when it was OCV, the production drops, right? And then as soon as we feed this 80% hydrogen, CO2, then it starts producing again, and it stabilizes around 2.5 gram per liter. And the columbic efficiency for this whole process remains around 38, 35, and 34 around percentage. So that's first batch. It produces acetate. And another thing is with 80% CO2, what we see is it's not producing more acetate, but it starts producing some butyrate and ethanol. So we repeat the same experiment for a second batch with a new electrolyte, but 80% CO2 is fed through the electrode. Here also we see production of acetate, and continuously this butyrate was also produced, but not much as before. But what you see is because of pH effect probably. When the pH goes down, then the acetate becomes inhibiting the bacteria, and they start converting into butyrate. So maybe that's the reason it's at a low pH, it starts producing butyrate. Yeah, but this is also the efficiency of production. It's also 32%, and the production, the concentration goes to 2.5 gram per liter. And this is a picture for the same images of the electrode after the experiment, and we see a lot of bacteria attached in the electrode. Okay, and now the second one. So this is a story about this gas diffusion. Now this is the flow-through electrode. Yeah, this is the as already I mentioned, it's like the CO2, the catalyzed fluid. It goes through there, and then it flow across the electrode, and it comes out. So this is the electrode that we use. It's just a simple carbon felt with a stainless steel in the middle. And also in the same way, we can see here the production, acetate concentration, the black curve. It's also we see it's a production here, but in this experiment, what we did is we didn't apply we didn't control the cutoff potential, but we apply cell voltage. So this the cell voltage of 3.1 volt. So in this case, we see the current start increasing at 3.1 volt, and the production starts here, and then it's also stabilized. It went up to 2.2 gram per liter, similar like the previous one. And we again see the pH dropping because of the production of acetates. And in this one, the production of butyrate is much more than before. Maybe it's because low pH. The pH was quite low in this case. Okay, and then from all of the experiments, what we can conclude is gas diffusion electrodes are really applicable for CO2 reduction, as it can dissolve the CO2 much better than the conventionally what we are doing before. And then if we use CO2 in such a way, then the pH, the microbial community, and the product spectrum, they are different than what we are doing conventionally. Like we can go for much important or more valuable product like butyrate, butanol, or much more. And this system is very effective for continuously operating. Like if we scale up and we want to use it continuously in industrial scale, then this system is much more effective. And also it is effective for waste gas, because we already saw it's 20%. CO2 is also enough to produce the 2 gram per liter of acetate. So with this conclusion, what we can see in the future, why don't we can start kind of a big industry with such an electrode, and we start CO2 as a feedstock, and we can produce a lot of chemicals. That's what we are called. It's like the name we give it a CO2 electro refinery. And that's kind of scheme we see in the future. And right now, the production facility that we have in our in Vito, this is the production facility for the gas for the electrodes, and we are currently doing the experiment with this, and hope in the future the experiments produce much more valuable and high amount of products. So that's still we are developing the process, and hope we can come this industry into reality. And with this, I would like to thank all my supervisors from Vito and from Wageningen. And thank you. And if any questions, please, I'm always open for questions.
All right, time for questions. Yes, please. Can you come over here? Or, okay, you're taking it. Okay, that's good. Yeah.
So did you observe methane formation in your process? Anyway, Coulombic efficiency is around 30,000%,
yes, true.
Where the rest goes.
Oh yeah, that's a good question. But I already told, I just showed the slide that We did heat shock at 90 degrees centigrade, so that's already killed all of the heat intolerant. So that's why we didn't get any methane. But the rest of the electrons, that's 32%. That means it goes into hydrogen. So there was a lot of hydrogen produced because we apply more potential than the minus 0.6. So it's hydrogen is there, and it's either it's used by bacteria, but most of them the hydrogen is also escaping. So that's the main thing that it's not completely. We are developing more, so we hope we can get to more 100% efficiency.
But in the preliminary experiments, yes, there was methane produced. When there was no heat shock given to the inoculum before putting into the cell, we did some methane production, yes, but not in these experiments. Any other question? Yeah, please. Sebas, yeah.
Sebastián Puig, University of Girona, Spain. I'm wondering about, for you, which is the main point to drive the reaction to butyric production or ethanol production instead of acetate. In your presentation, you say something about the pH.
Yeah.
Can you go further on that? Do you have another guess?
Yeah, my guess right now it's only probably pH, because at low pH there's acetate. They change it into acetic acid form. So that acetic acid might be the things that switch the bacteria into the because it becomes a kind of toxic, or it's inhibiting effect. So that inhibiting effect turn it into this butyric production. Maybe this it's called something like a chain elongation reaction. Yeah, so that's probably that's pathways keep on that's trigger because of pH. So that's maybe that's the reason it went to butyric.
I have a technical question about the anodic reaction. So your estimation of the anodic reaction is oxygen production.
Yes.
But in my feeling, it's really difficult to make that kind of thing. So do you have a special catalyst or that kind of thing?
Yes, we use a platinum in that
Platinum,
case.
okay.
Yeah.
And then you confirm oxygen produced.
Yes, oxygen produced, and that's we can see the evolution of gases and the
The
reactor.
bubbling or your picture or your image
Yeah.
suggests the oxygen is outside reaction, but
Oh,
it might
means-
be bubbling inside, right?
Yeah. It's just coming out from the reactor. Yeah. Okay.
Any other question? Okay, if not, then we can close this talk and move to the next speaker, who is